2008, civilization reached a global milestone. For the first time in human history, there were more people living in urban areas than in rural ones. We have become a species that primarily lives in cities. And to make these cities function, we need power. Electricity and alternating currents greatly facilitated or even enabled this shift. But we use power to do more than just to keep the lights on or to keep our computers humming. We also use it to move ourselves and our possessions across vast distances, and even to power every single cell in our bodies. In the next 2 lectures, we are going to explore the concept of power in both the animate and inanimate worlds, in machines, as predicted by the laws of thermodynamics, and in the next lecture, in cells, as represented by metabolism. Harnessing the power of our world and our bodies has arguably enabled the biggest changes in human civilization. We are now able to cross vast distances in a short period of time. We are no longer limited to working during daylight hours. We can survive in extreme temperatures by regulating our environment, and we can power our bodies even when our brains are no longer functioning. Starting with machines, we'll soon discover that the laws of thermodynamics describe the relationship between heat and work, and their application has provided us with every vehicle we've ever used. Machines demonstrate thermodynamics from the perspective of mechanical engineering, but chemical engineering departments also teach thermodynamics. So in the next lecture, we'll look at chemical equilibrium and how the laws of thermodynamics also apply to the energy exchanges that occur within each one of our cells. These days, any mention of energy brings up 2 very different visions. First, the needs of a modern world for which we are willing to go to war or destroy our environment, or make billions of dollars delivering to an avaricious public. Our craving for oil and other sources of energy underscores the critical role that thermodynamics plays in our lives. And second, the New Age notion that many of our interactions with each other and our world are invisible and take the form of energy that we can feel but not see. There are still plenty of aspects of energy that we don't fully understand, but it's using careful and rigorous scientific inquiry that has allowed civilization to progress as rapidly and prolifically as it has in the past centuries. As eminent physicist Stephen Hawking has said, science will win because it works. As such, the term energy is fraught with connotation, and even in physics, where defining terms is the key to studying them, there is no simple definition of energy. Even Einstein's famous E equals mc squared equation shows the relationship between energy and mass, but doesn't define energy itself. Instead, we talk about work, which is the energy transferred from one system to another. Work powers things by moving energy from one place to another. And energy is often released in the form of heat. So thermodynamics, from the Greek words for heat and movement, involves understanding how heat is harnessed to power both the mechanical and natural worlds. The history of modern thermodynamics is often said to start with a publication by Nicolas Léonard Sadi-Carnot, the father of thermodynamics, and a French military engineer and physicist. He only wrote 1 book, published in 1824, called Reflections on the Motive Power of Fire. But with it, he ushered in a new scientific discipline, outlining how an idealized engine might function. From the outset, the theories and laws of thermodynamics have been virtually inseparable from their applications. So when we want to learn about the concept, we need to understand the machines and the engines that use it. The title of Carnot's seminal work underscores the central relationship that defines thermodynamics. That is, the relationship between heat, or fire, and motion, or how heat powers things. What is heat? Heat is energy that flows from a higher temperature to a lower temperature, often across objects in contact with one another. We measure heat in joules. We don't say that an object contains heat. It has a particular energy, but unless the heat is moving from one place to another, it's not heat. Heat moves from coffee in a mug to the mug itself to our hands as we hold it. Now, when the temperature of an object stays steady and there is no net flow of heat from one area to another, we say that the object has reached thermal equilibrium. But how do we measure the temperature of an object? Well, here we have the application of what's called the 0th law of thermodynamics. It's called the 0th law because the first and second laws were stated first in the 1850s. It wasn't until the 1930s that the 0th law got its name. But it's the simplest of the laws and hence precedes the others. The 0th law states that if two bodies are independently in thermal equilibrium with a third body, they are in equilibrium with each other. That is, if you put a thermometer in 2 glasses of water and it reads the same temperature, then the 2 glasses of water are equally hot. Simply put, all heat is of the same kind. Sounds pretty simple, and it is, but it's an important assumption that we make so that we can use a thermometer to measure temperature and therefore predict the flow of heat. Why do ice cubes keep drinks cool, even after the cubes and the liquid are at thermal equilibrium, when the surroundings of the drink, such as the room, is at a higher temperature? Because the heat in the surroundings or the room is being used to do the work of melting the cubes, not to raise the temperature of the liquid. The liquid's temperature will only rise once the cubes are melted. Here you have the 3 bodies of the 0th law: the ice, the water, and the room. So now that we've covered the 0th law, let's jump right to the most closely related law, which is the 3rd law of thermodynamics. This law was formulated after the first and second laws, and so it's called the 3rd. But for our purposes, it's more convenient to discuss it now since it's most closely related to the 0th law. The 3rd law states that it's impossible to reach a temperature of absolute 0. Let's unpack this one. First, what's absolute 0? Well, simply put, it's the coldest possible temperature. How do we know what the coldest temperature is? Because it represents the edge of what's physically possible. At absolute 0, all molecular motion stops. A British physicist and engineer, William Thomson, the first Baron Kelvin, devised a temperature scale whose lowest value is absolute 0, which translates to about negative 273.15 degrees Celsius. But the 3rd law states that it's impossible for something to reach absolute 0. Why? Because heat flows from hot to cold. So the surroundings of something going to 0 need to be less than absolute 0, which, of course, is impossible. So the 0th and 3rd laws are about temperature. One states that you can measure it with a thermometer, and the other states that an object can never reach absolute 0. Arguably, one of the most dynamic times in all of civilization was the Industrial Revolution from about 1760 to 1840. In the span of less than a century, humanity saw a shift from using men and animals to perform work to the use of machine tools, steam-powered ships and trains, and new chemical manufacturing. It was the beginning of the end of aristocracy, as average incomes showed unprecedented growth. And while the details of the revolution are dense and complex, the Industrial Revolution in a nutshell was possible because we figured out how to put heat to work. What makes thermodynamics unique in the sciences is that the applications of the field have largely driven the study itself, rather than curiosity about the world. In other scientific fields, curiosity about something natural generally sparks the work, which is then applied to make our lives better. But in thermodynamics and its closely related cousin, fluid mechanics, the opposite is true. We wanted to figure out how to power things and set big objects in motion, and we discovered the laws of thermodynamics in the process. And so, to understand thermodynamics, we turn to the applications first and foremost. To that end, let's consider how an ideal engine works. To understand how an ideal engine works, we have to assimilate the remaining two laws of thermodynamics. The first law is that of conservation of energy, though it applies to mass as well. Energy cannot be created or destroyed in an isolated system. This means that energy in a system can only change form, say from heat to work or vice versa, but you can't add it or subtract it. It has to come from somewhere in the system. The second law states that heat flows from hot to cold and never the other way around. To get something to go from cold to hot, then, requires work. The second law is often also stated in terms of entropy, or the state of order in a system. Using this framework, the second law states that a system is always moving towards maximum entropy. Life devolves into chaos. When we talk about thermodynamics, we're really interested in how a particular system works, whether it's an ocean or a car or a thermometer. So we divide up the world into a system and its surroundings. For example, if we want to understand how ice cubes cool a glass of tea, we think of the cubes as the system and the tea as its surroundings. But we can go further and think about how the glass gets colder as the tea chills. So in that case, the liquid and the cubes are the system and the glass is the surroundings. Or we can zoom out even further and talk about the glass full of tea and ice as the system and the room it's in as the surroundings. In each case, we have a number of different variables to consider when we are analyzing the thermodynamics of an object. We need to be clear on what we're calling the system and what is defined as its surroundings. We can also have open or closed systems. In an open system, there is heat or workflow into and out of the system, like a dam, which is constantly replenished by a water source somewhere else. In a closed system, there is no movement of heat, work, or energy into or out of it. It's completely isolated. Most systems aren't, of course, but for our purposes, it will sometimes be most effective to think of a particular system as theoretically closed. In a closed system, we can create what's called an ideal engine. Our paternal French military engineer, Sadi Carnot, proposed in 1823 that a maximally efficient heat engine has one important property. All the processes within the engine must be reversible. That is, when both the system and its surroundings are returned to their original states after the process has occurred, we say that it's reversible. We know then that a car's engine is not ideal because heat escapes and because processes within the car cause friction which dissipates energy. Now note that the opposite isn't true. A reversible engine may not be maximally efficient. The law only goes in one direction. Perhaps the best way to imagine a Carnot engine is to think of a system in which heat comes from a hot reservoir, powers the engine, and then rejected heat or unused heat flows into a cold reservoir. And the engine itself has some unique features. There's no friction, so no energy dissipates that way, and the hot side of the engine is the same temperature as the hot reservoir, and the cold side of the engine is the same temperature as the cold reservoir. Now, when you think about it, a refrigerator is just a basic Carnot engine with all the arrows pointing in the reverse directions. Work goes in to power the engine that in turn draws cold from the cold reservoir and sends it to the hot reservoir. So the cold reservoir is the inside of the fridge and the hot reservoir is somewhere outside of it. Carnot's principle also demonstrates why you can't cool your kitchen by leaving open your fridge door. You'd have to somehow have the heat dissipate outside of the room. In order to understand how the laws of thermodynamics enable us to power our lives, it's useful to concentrate on two types of engines that are perhaps the most famous examples in thermodynamics. The steam engine in old trains and ships, which is an external combustion engine, and our car engines, or an internal combustion engine. Let's start with steam engines, since they were the first to be widely used, and improvements to the steam engine ushered in the Industrial Revolution. And they didn't just power boats and trains, they were also responsible for powering many factories. So what are the major components of a steam engine? First, you need a piston attached to a rod and placed inside a cylinder. The movement of this piston is what moves the train, boat, or whatever forward. What causes the piston to move is the hot air in the form of steam. So then you need a place for the excess steam to exit and a place for the high-pressure steam to come in. You also need a way to heat up the steam. You need a boiler. A boiler is simply a furnace that heats up the water. There are two main types. In a fire tube boiler, pipes run hot gases from the fire through a vat of water, whereas in a water tube boiler, more common these days, the hot gases heat a series of tubes of water. The steam leaving the boiler is at a very high pressure, and when the engineer opens a valve to let that steam travel down to the piston chamber, it causes the piston to move in one direction. There is another valve attached to the piston chamber that moves when the piston is all the way at the other end of the chamber. When that valve moves in the opposite direction, it lets out excess steam, which causes the piston to move back to its original position. This way, the pressure from the steam moves the piston back and the valve moves it forward. This is why excess steam is let out of the chimney and also why trains make the choo-choo sound. As the steam escapes, it goes choo. When the train is first leaving the station, its pistons are moving slowly, but eventually they speed up and we hear choo, 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 choo. So, as the laws of thermodynamics state, heat is used to do work. The steam from the boiler eventually moves the train forward. In a steamboat, the pistons are attached to a paddle wheel rather than the wheels of a train, but the same general principles apply. Steam engines are external combustion engines because the combustion that generates the heat that creates the work occurs outside of the engine itself. Internal combustion engines are much more efficient and therefore can be a lot smaller, making them ideal for vehicles such as cars. Now, the inventors of the internal combustion engine noticed that much of the potential energy in the furnace that heats the water in a steam engine is wasted. Instead, if you ignite even a small amount of fuel in an enclosed space, a very large amount of energy is released, and you can use that energy to put something else in motion. Once again, heat is used to create work. That's the fundamental principle underlying a car engine. Let's get to the details. In 1867, a man by the name of Nicholas Otto invented the four-stroke combustion cycle to convert gasoline into motion. The strokes refer to the movement of the piston up and down the cylinder, which goes through 4 strokes in each cycle. The first one is the intake stroke. The piston moves downward to let the engine take in a cylinder volume of air and a tiny amount of gasoline. Then, during the second stroke, the piston moves back up to compress the fuel-air mixture, ensuring that the explosion will be more powerful. At the top of the third stroke, the combustion stroke, a spark plug emits a spark which ignites the fuel and drives the piston down. Then the fourth stroke opens the exhaust valve so that the exhaust can leave the cylinder and go out the tailpipe. So we see how a combustion engine uses the principles of thermodynamics to move a car forward. Gasoline is converted into motion. But there's another type of engine that's far more powerful. Thermodynamics on steroids, if you will. The turbofan engine, a type of gas turbine that powers commercial jets. And so to understand how thermodynamics can scale up, we turn to turbine engines. Besides gas turbines, there are three other main types of turbine engines: steam turbines, water turbines, and wind turbines. You're probably somewhat familiar with all of these. Coal, natural gas, and nuclear power plants all create steam and run it through a massive turbine to spin some kind of shaft that drives an electricity generator. A turbine is a mechanical device that rotates and extracts energy from the steam to move the shaft. Hydroelectric plants use water to power the turbine, while wind turbines are, of course, moved by the wind. Now, in a gas turbine, essentially the same concept applies. A pressurized gas spins the turbine, which creates work and drives some component. In a jet engine, heat from burning jet fuel expands air, and this fast-moving hot air spins the turbine, which we see under the wings in commercial airliners. Why use jet fuel? Undoubtedly, it's expensive, which is why many flights these days seem to take longer than they used to 10 years ago. The commercial airlines are saving costs by using less jet fuel on longer flights. But the amount of power that you get in a jet engine for its weight compared to a traditional engine is much greater. Gas turbine engines are also much smaller than other engines. A gas turbine starts with a rotating device with spokes that takes in outside air and compresses it, sending it to the combustion chamber behind it. There, the fuel is burned, and then the turbine, located behind the combustion chamber, extracts the pressurized, fast-moving gases and moves the output shaft. In a turbofan engine, the shaft is connected back to the front of the engine, where it powers a big fan, the blades that you see when you look at the front of a jet. This fan dramatically increases the amount of air moving through the engine and increases its thrust, a concept we'll be covering in the upcoming lectures on fluid mechanics. It's the thrust that moves the airplane forward, but we'll get to that later. In all of these examples, the laws of thermodynamics are applied to turn heat into work and to keep us moving. But there are other uses for thermodynamics, including helping us understand and predict the effects of climate change on our planet. In 2005, Hurricane Katrina ripped through the Gulf of Mexico and became one of the costliest natural disasters in U.S. history. More than 1,800 people died as a result of the storm, and property damage has been tallied at a whopping $81 billion. Another costly storm, Hurricane Sandy, hit the Atlantic coast in 2012, causing more than $68 billion in damage and killing 286 people. Whether human activities that cause global warming have also triggered an increase in the rate and size of hurricanes remains unclear, but the odds are not in our favor. What's very clear is that flood insurance and other costs associated with owning property in the path of hurricanes is most definitely increasing. And if we follow the money, as it were, there is clearly something going on. In the context of thermodynamics, hurricanes are particularly interesting because they are said to represent almost perfectly efficient Carnot engines. Unlike our cars and ships and jets, hurricanes waste very little energy. For example, a car is thought to function at about 25% efficiency. Much of the heat in the engine is lost, and we can easily experience this fact by placing a hand on a running engine. Now, really don't try this at home because there are many parts of the engine that will burn your hand to a crisp since so much heat is being lost. But a hurricane transforms heat into work much more efficiently. So much so that a tropical cyclone, of which hurricanes are one form, can release heat energy at a rate of 10 to the 15 watts. That's about 70 times the daily world energy consumption of all of humanity. 200 times the worldwide electrical generating capacity, or the equivalent of setting off a nuclear bomb every 20 minutes for the life of the storm. This heat energy is turned into rain via condensation and into wind energy as the strong, swirling winds that cause the characteristic shape photographed by orbiting satellites. A cyclone gets its energy from the evaporation of water from the ocean's surface. This is why we only see Atlantic hurricanes at the end of summer, when the ocean is the warmest, and not at all near colder regions like Alaska and northern Canada. In our Carnot version of a hurricane, heat from the oceanic reservoir flows into the eye of the hurricane, typically circular in shape, which can range from 3 kilometers, about 2 miles, to a whopping 370 kilometers, or 230 miles in diameter. In the eye of the hurricane, the weather is generally mild and cloud-free, though the ocean below is usually whipped into a frenzy. Along the eye wall, or the sides of the eye, the latent heat from evaporation is turned into sensible heat. Latent heat simply means that it's hidden in the sense that no temperature change is detected. The temperature change that happens then is that the heat is turned into sensible heat during condensation. The evaporated water now in the air condenses into rain as the air rises and cools. The rotating pattern in the winds that is typical of cyclones is actually caused by the angular momentum of the Earth, what is known as the Coriolis force. This force is what causes hurricanes in the northern hemisphere to rotate counterclockwise towards the north first, then west, and cyclones in the southern hemisphere to rotate in the opposite direction, clockwise, pulled south before being blown east. Essentially, hurricanes take heat from the ocean, transfer it into rain and wind, and move it along their path of destruction. Once they hit land, they dissipate quickly because there is no more heat to feed them. But the devastation that they leave behind in the form of floods and winds is legendary. It's not just humans that have learned to harness heat to power work. Mother Nature has sorted it all out far more effectively than anything that we've created. And time will soon tell if our man-made energy uses have given her more power in the form of global warming. In 2006, the U.S. National Oceanic and Atmospheric Administration Geophysical Fluid Dynamics Lab, now that's a bit of a mouthful, predicted that, and I quote, "the strongest hurricanes in the present climate may be upstaged by even more intense hurricanes over the next century as the Earth's climate is warmed by increasing levels of greenhouse gases in the atmosphere." Now, if we could only figure out how to harness the energy of a hurricane for less destructive purposes. We started this lecture by getting an understanding of the relationship between temperature, heat, and work, and then moving on to the laws of thermodynamics, exploring how engines apply these laws to power our vehicles, and finally, how the laws of thermodynamics can help us understand some of the most powerful storms in nature. But it's not just machines and the environment that use heat to power work. Every one of our cells is a tiny Carnot engine of sorts. We turn nutrients into fuel that our cells use to accomplish the vast diversity of functions of which they are capable. Metabolism, which we turn to next, is how our bodies use thermodynamics to keep us alive.